In this video, I'd like to talk about how to initialize k-means, and more importantly, this will lead into a discussion of how to make k-means avoid local optima as well. Here's the k-means clustering algorithm that we talked about earlier. One step that we never really talked much about was this step of how you randomly initialize the cluster centroids. There are a few different ways that one could imagine using to randomly initialize the cluster centroids, but it turns out that there's one method that's much more recommended than most of the other options one might think about. So let me tell you about that option, since it's what often seems to work best. Here's how I usually initialize my cluster centroids. When running k-means, you should have the number of cluster centroids k set to be less than the number of training examples m. It would be really weird to run k-means with a number of cluster centroids that's equal or greater than the number of examples you have, right? So the way I usually initialize k-means is I would randomly pick k training examples. What I do is then set mu1 up to mu k equal to these k examples. Let me show you a concrete example. Let's say that k is equal to 2, and so on this example on the right, let's say I want to find 2 clusters. So what I'm going to do in order to initialize my cluster centroids is I'm going to randomly pick a couple examples, and let's say I pick this one and I pick that one. And the way I'm going to initialize my cluster centroids is I'm just going to initialize my cluster centroids to be right on top of those examples. So that's my first cluster centroid, and that's my second cluster centroid, and that's one sort of random initialization of k-means. The one I drew looks like a particularly good one. Sometimes I might get less lucky, and maybe I'll end up picking that as my first randomly chosen example, and that as my second one. And here I'm picking 2 examples because k equals 2. So I'm going to randomly pick 2 training examples. And if I chose those 2, then I'll end up with maybe this as my first cluster centroid, and that as my second initial location of the cluster centroid. So that's how you can randomly initialize the cluster centroids. And so at initialization, your first cluster centroid, mu1, will be equal to xi for some randomly value of I, and mu2 will be equal to xj for some different randomly chosen value of j, and so on if you have more clusters and more cluster centroids. As sort of a side comment, I should say that in the earlier video where I first illustrated k-means with an animation, in that set of slides, only for the purpose of illustration, I actually used a different method of initialization for my cluster centroids. But the method described on this slide, this is really the recommended way, and the way that you should probably use when you implement k-means. So as is suggested perhaps by these 2 illustrations on the right, you might really guess that k-means can end up converging to different solutions depending on exactly how the clusters were initialized. And so depending on the random initialization, k-means can end up at different solutions. And in particular, k-means can actually end up at local optima. If you're given a data set like this, well, it looks like there are 3 clusters. And so if you run k-means, and if it ends up at a good local optima, this might be really the global optimum, you might end up with that clustering. But if you had a particularly unlucky random initialization, k-means can also get stuck at different local optima. So in this example on the left, it looks like the blue cluster has captured a lot of points on the left, and then the red and the green clusters each is capturing only a relatively small number of points. And so this corresponds to a bad local optima because it has basically taken these 2 clusters and merged them into one, and furthermore it has split the second cluster into 2 separate subclusters like so. And it has also taken the second cluster and split it into 2 separate subclusters like so. And so both of these examples on the lower right correspond to different local optima of k-means. And in fact, in this example here, the red cluster has captured only a single unlabeled example. And the term local optima, by the way, refers to local optima of this distortion function j. And what these solutions on the lower left, what these local optima correspond to is really solutions where k-means has gotten stuck at the local optima and is not doing a very good job minimizing this distortion function j. So if you're worried about k-means getting stuck in local optima, if you want to increase the odds of k-means finding the best possible clustering like that shown on top here, what we can do is try multiple random initialization. So instead of just initializing k-means once and hoping that that works, what we can do is initialize k-means lots of times and run k-means lots of times, and use that to try to make sure we get as good a solution, as good a local or global optimum as possible. Concretely, here's how you could go about doing that. Let's say I decide to run k-means 100 times. So I'm going to execute this loop 100 times. And a fairly typical number of times to run k-means would be something from 50 up to maybe 1,000. So, but let's say you decide to run k-means 100 times. So what that means is we would randomly initialize k-means, and for each of these sort of 100 random initializations, we would run k-means, and that would give us a set of clusterings and a set of cluster centroids. And we would then compute the distortion J, that is compute this cost function, on the set of cluster assignments and cluster centroids that we got. Finally, having done this whole procedure 100 times, you will have 100 different ways of clustering the data. And then finally, what you do is, out of these 100 ways we've found of clustering the data, just pick one that gives us the lowest cost, that gives us the lowest distortion. And it turns out that if you're running k-means with a fairly small number of clusters, so if the number of clusters is anywhere from 2 up to maybe 10, then doing multiple random initializations can sometimes make sure that you find a better local optimum, make sure that you find a better clustering of the data. But if k is very large, so if k is much greater than 10, certainly if k were, if you're trying to find hundreds of clusters, then having multiple random initializations is less likely to make a huge difference, and there's a much higher chance that your first random initialization will give you a pretty decent solution already, and doing multiple random initializations will probably give you a slightly better solution, but maybe not that much. But it's really in the regime of when you have a relatively small number of clusters, especially if you have maybe 2 or 3 or 4 clusters, that random initialization could make a huge difference in terms of making sure you do a good job minimizing the distortion function and giving you a good clustering. So that's k-means with random initialization. If you're trying to learn a clustering with a relatively small number of clusters, 2, 3, 4, 5, maybe 6, 7, using multiple random initializations can sometimes help you find much better clusterings of the data. But even if you're learning a large number of clusters, the random initialization method that I describe here, that should give k-means a reasonable starting point to start from for finding a good set of clusters.